Okay, welcome to another Stat 510 video. In this video, we're going to talk about estimating a distribution function and this thing called statistical functionals. So in contrast to our previous video, which was a very broad overview of statistical inference, we're going to be talking about basically one estimation and follow-ups to it in this video. Although while it's a very specific idea, it also has very general applicability. So let's take a look. So we're going to be living in the setup that we keep talking about where we have x1 through xn, which is a random sample from some distribution f. So first I should say that we're going to assume the practical situation where we don't know f. If we knew f, we knew the distribution that these data came from, I mean, I should just quit, right? Like, we don't need statistics anymore. The math people can take over and do all the probability, and I can go retire or, I guess in my case, find some new profession, right? If we knew the distribution, we wouldn't need statistics. Okay, but practically speaking, we almost never know the distribution the data came from. So what do we want to do? Well, the first question is, how do we estimate that distribution? So that's the first question we're going to answer in this video. The other question we're going to answer is how to estimate what I'm going to call properties of that distribution f. So while in this video we're going to focus mostly on estimating that distribution, oftentimes we're interested in more specific features or properties of that distribution, like say a mean or a variance, that kind of thing. But that's sort of a follow-up question in this video to the larger question, which is, well, how do we actually estimate f? So let's jump into it. So the idea, which is actually pretty natural and straightforward, and you've probably perhaps used this idea without someone even giving a name to it before and you starting realizing it, is something called the empirical distribution function, which we denote f hat sub n. So this empirical distribution function is literally a CDF, and what it does is it places a mass 1 over n at each point xi. So that's one way to think about it. More formally, we can define the function itself. And what this essentially is saying, if we want to find the CDF at some value x, well, sum up the number of observations that are less than that x and divide by how many observations they were. So it's basically the proportion of observations that we observe that are less than or equal to the particular value that we want to evaluate the CDF at. So that's pretty straightforward. It's a very natural estimator of the true distribution function f. So let's look at an example. So here, I made it really easy on myself, and I said, well, we observed 5 data points, 2.1, 1.3, 3.4, 2.5, and 1.7. And so to calculate the empirical distribution function, which I already did, but the first step sort of as a human to do it is you would want to sort the data. So I think we go 1.3 and then 1.7 and then let's see, 2.1, 2.5, and lastly 3.4. Right? So before we even get down to the answer that I wrote here, so for example, like let's say I wanted to evaluate f hat sub n, well I guess there's really no n here, it's 5, but okay, of, let's say, 3, right? Well, 3 is right about here. So there's 4 observations that are less than 3 and 5 total observations for 0.8. And if we come down here, we see that 3 is in there, and this would output 0.8. So notice that we defined all these different regions, but we went from 0 to 0.2, 0.2 to 0.4, 0.4 to 0.6, 0.6 to 0.8, 0.8 to 0.1. So we're always just jumping up. So what we really have here is a step function that we're dealing with. So I'm gonna try to draw it now. Let's see if I can do this freehand. So what I have along the x-axis, sort of conveniently, is the values of the observations that we saw. So below 1.3, we didn't see any observations, so the CDF returns 0. And then at 1.3, there's a jump because we put 1 over n mass there, so 1 over 5. So we jump up to 0.2. And then until we see our next observation, the CDF stays flat, constant, until we get to this 1.7, and then we jump again. Sorry, the y-axis is not, neither of these axes are to scale. But the point is that it's a step function. So then at 2.1, we have a jump to 0.6, and so on and so forth. And then the last thing that we observe is 3.4, so that's when the probability hits 1. And then for any values bigger than 3.4, the CDF returns 1. So that's the idea. Obviously, this is not something that you're going to want to do by hand. You're going to want to do this in a computer, but more on that in a minute. Okay, so this empirical distribution function has some really nice properties. So for a fixed x, the expected value of the empirical distribution function is the value of the actual distribution function. The variance of the empirical distribution function evaluated at some value x turns out to be this expression we see here. And as a result, because essentially the first line tells us that it's an unbiased estimator, that together with the fact that the variance has this nice 1 over n, says that as n goes to infinity, the mean squared error goes to 0. And then it also turns out that the empirical distribution function converges in probability to the true distribution function. Now I could sit here and prove all of these, but instead we'll do proof by exercise to the reader. But I would note that hopefully you already see some familiar things here. So what is f hat? But it's the sum of a bunch of random variables that output 0 or 1. And if we knew f, which we kind of have to assume to do these calculations, well, we could attach a probability to this thing here, right, for a fixed x. So for a fixed x, the xi are either below or above it, and then we're averaging them. That should maybe sound familiar. And then maybe I'm going to call this thing here, the probability p. Well, if this is p, then this thing here is kind of 1 minus p. So hopefully this is some light bulbs are going off. Oh, this looks familiar. So when you do this, kind of reduce it to something you already know is the suggestion. But these are some useful properties of the empirical distribution function. Okay, moving on. So a couple quick theorems. So this is I'm going to not say this name right, Glivenko-Cantelli theorem. So it says that if we're in the usual setup, then essentially what this is saying is the x that gives the biggest distance between the empirical distribution and the true distribution, that converges in probability to 0. So essentially, as n gets bigger, the probability that these two functions will output, wildly different numbers, just shrinks, which is great. So that's useful. Next, we have the DKW inequality. D, K, and W are three names that I'm not even going to attempt to write because I will not only mispronounce them, I will also misspell them, but it's in the book. So this, again, in the usual setup says, okay, so if we have some epsilon bigger than 0, then the probability that the biggest possible difference between the empirical and the true being bigger than some possibly arbitrary small epsilon is bounded above by this thing. And this should sort of make you think back to Hoeffding's inequality. But so we're going to use this now to create confidence, what we call bands, for the empirical distribution function. So So we want to. So one thing I should say here: what we're doing is non-parametric estimation, right? So we have made no assumptions about f whatsoever, except that it is a CDF. And the way we defined the empirical distribution, well, we know that has to be a CDF at the end of the day because we have n observations, and each one is given whatever n mass. That's always going to sum up to 1. So it's a valid CDF, but that's the only thing we're assuming. Okay, so now we want a 1 minus alpha confidence band for f. So basically what we want, if we go back to this picture here, is I want, so like well, that would be silly, actually. So we'd want it to maybe do something, and it would be not smooth, but okay. Yeah, this is not a brilliant picture. I should probably do it like this. Something like that, maybe. So what we want is bands around the actual function such that the function itself is contained within it. Oh, I should note that oftentimes when people plot these, they have these vertical lines like this. So you really see that it's a step, and you can really see that it's in between the bands. The bands themselves will often be step functions too, but I'm just showing that the empirical distribution function. Oh, sorry. Oh gosh. So this picture is terrible. Forget I tried to draw the picture. I'll show you a good one in a second. I should have never attempted to freehand that. Okay, but anyway, I need to move this. Okay, so we want it to be bands. So basically, we're going to have our empirical distribution function, and then we're going to sort of bound it above, bound it below, and then that band hopefully contains the true CDF within it. Okay, that was the explanation, but we'll still get to a picture that'll describe this. So basically what we do is we sort of define this sort of margin of error thing, which you can probably see where that's coming from. And then the lower and upper bounds of these bands, which are now a function of x because we're going to have to plot it for all possible x. But note that we never let the lower bound go below 0 because we're trying to bound a CDF, right? So that kind of makes sense. And we never bound what would be the upper. We never let what would be the upper bound go above 1. So if this turns out to be like 1.3, we instead output 1 because we don't need to go above 1 because it's a CDF. And then all this together, if we apply the DKW inequality, we get a probability that the lower bound and upper bound together for any x contain the true value of the distribution function is greater than or equal to 1 over alpha. Okay, so what does this look like? It looks like this. Okay, so what do we have here? So what I did is I went into a computer and I simulated data according to a standard normal distribution, and I simulated 27 observations. So the orange curve here is a normal 0, 1 curve. So that is the true distribution function. The black, that is f hat sub n of x. So that's the empirical distribution function. So the blue, well, here is the upper bound of x, and below it, maybe I should write it over here, except you can't see that. Anyway, so this here is the lower bound of x. Okay, so we have our estimate, and then at any x, we have, plus minus a margin of error. But note that these bands, they're not point-wise confidence intervals. They're across the whole possible x values confidence interval. So that is, if we repeatedly did this process, the entire true function would be contained within the bands, not like, every x individually has a 95% confidence on it. It's the whole function is going to be within the bands, 95% of these intervals. I should say that this is a 95% CI, but that's not super important. Just to understand visually what's going on. Okay, so that's cool. So we can estimate any distribution function with this one simple thing, and then we can also put bounds around that too, so we can estimate it with uncertainty. So that's pretty neat. Okay. But so let's build on this idea. So I want to put forward this notion here. So I've utilized the old SAT analogy syntax here, which says that I want to say that a parameter is to a distribution what a statistic is to data. And I'm playing a little bit fast and loose with all of the definitions here, but I'm just trying to get across a generic idea. So I think at this point, everyone would agree with me that a statistic is a function of data. What I want to get across is that similarly, a parameter, and I'm loosely defining parameter here, is a function of a distribution. Okay, so I want to use this idea now to estimate properties of a distribution instead of just a distribution. So basically, long story short, we already estimated the distribution, right? So now I want to estimate what I'm going to call parameters. I'm going to give them a different name in a second of that distribution. And it turns out that if we can estimate the distribution, we have a generic way to just go ahead and estimate parameters of that distribution. That is functions of the distribution. So I want to introduce the correct nomenclature here, which is what we will call a statistical functional. So if we have some function t of f, so it's a function of the distribution function, we say that is what's called a statistical functional. So, and you've seen a bunch of these before, right? So the mean, mu, is a function of f. Now, it's a goofy looking function, right? So we have this integral here, but like any function, if you change the input, it changes its output, right? So if we supply a different f, we're going to get a different output. So that is indeed a function of f. So similarly, we have the variance, and we could also consider the median. So the median is just if you invert the CDF and then insert the probability 2, it'll output the value that gives you half the area to the left of it. So those are all functions of f, the distribution. So those are what we call statistical functionals, and we would like to estimate them. So it turns out there's a really nice way to do it, and it's called the plugin estimator. So if we have some theta, that is a parameter, I guess, of interest, that we're defining to be some function of the distribution, well then the plugin estimator is just that function, but instead of applied to f, you apply it to the estimated distribution. So in other words, you will, Dave will spell correctly, you will plug in f hat for f. So basically, we reduce the problem of estimating any function of a distribution to just first estimating the distribution. Then we apply the plugin estimator, and then we're done. Okay, cool. So one definition before we... Oh gosh, that's not what I wanted to do. One definition before we see a couple examples here is this notion that if t of f can be written in this sort of integral form, where it's the integral of some function r of x df of x, that is for some r, then t is what's called a linear functional. And it's that way because t's that satisfy this have this property here. It looks like this. So this would be t of f plus b t of g. Okay. So when something is a linear functional, we'll see in a second here that makes life a lot easier. So let's have a look. So here we're going to assume that, assume t is linear. Okay, so let's say we apply a linear functional to an estimated distribution. So then this is just by definition So because it's a linear function, it has to linear functional. It has to follow this format where it's the integral of some r of x d, and then in this case f hat of x. And then this equal sign here is because don't forget that f hat n is discrete. Maybe we should just write it out. And when we're using this notation here, that allows us to deal with continuous and discrete random variables. But here we're dealing with a discrete random variable. So now we apply the definition of expectation of a discrete random variable, which says it's the sum of that r function times of xi times the individual probability mass functions for each xi. But in the case where we're dealing with f hat of n, well, this is just 1 over n for each, right? So, because again, so this equality here is because we have a point mass of 1 over n at each xi. So now we get this nice expression here. So it's literally just the average of the r of xi's. So that's pretty nice. One more idea before we look at examples finally. Okay, so something you might want to do is build confidence intervals for these estimates, right? So if the functional applied to the empirical distribution can be approximated by a normal distribution with the appropriate parameters. Importantly, the mean is the thing you're trying to estimate. Then a 95% normal CI, that idea that we talked about last time, is going to be approximately the functional applied to the distribution plus or minus 2, where 2 is 1.96, times the estimated standard error. I forget if we'll see an example of this, but I think you'll see where we're going when we look at the examples. Okay, so first example, the mean. So the mean is defined to be what we see here. So that is the function in our statistical functional. So if we want to estimate that, so we'll call it maybe mu hat. So all we do is apply that function to the empirical distribution. I don't really need to say all that. I can just do it like this. Okay, so we plug in. So we get x, d, f hat n of x. But this is a linear functional. So either by definition or we really could have skipped from here to here because we know we have a linear functional and we sort of showed earlier. But so then this is 1 over n sum of the xi. Because again, the function here, that r function is just the identity. And this is what we would call x bar pretty often. So I would note that often we know the variance of x bar is what? It's sigma squared over n, where sigma squared is the variance of an individual observation. I just haven't defined it that way. So that means that something like x bar minus mu divided by, let's see, sigma squared hat over n square root, in other words, the standard error. This thing is approximately normal 0, 1. So we could use that to make a confidence interval here. Okay, but, oh gosh. I don't really know if it's worth keeping my camera on, but I have so far, so I'm going to keep going. Okay, so this case here, we could even go as far as making a confidence interval because we can pretty clearly see how to calculate an estimated standard error. It's kind of no big deal. Let's look at another example, though. Let's say we wanted to estimate the variance. So I've written out the variance is some function of f. But again, I should probably swap these two, but that's okay. But so this is now a linear functional where this thing here is r of x is x minus mu squared. Except what I'm going to do is I'm going to split up that integral before I do that. So what we actually have is sort of two functionals now, where I can say this is r of x, and this is another r of x here. So this is just the mean here, because that's how this works. So if we keep going now, let's see. I want to say sigma hat squared. So our estimate for the variance is, well, plugging into this line here. So we get integral of x squared df hat of x minus integral x df hat and of x, that whole thing squared. And again, we could have jumped straight to here, realizing it was a linear functional, but I chose not to for whatever reason. So actually, I'm going to put this on a new line. So this is equal to 1 over n sum of the xi squared minus 1 over n sum of the xi, that whole thing, squared. And then with a little bit of algebra, we could show that this is equal to 1 over n sum of the xi minus x bar squared. And what you might notice is that this is not equal to 1 over n minus 1 sum of the xi minus x bar squared, which we would often call the sample variance. So, I mean, different estimation methods land you different estimators. So this is the plug-in estimate, and it's not the sample variance. But often we spend far too much time worrying about the difference between here and here. With a big N, it doesn't make much of a difference, so it's maybe not to worry. But something to think about here, well, what's the variance of sigma hat squared? I mean, perhaps we could figure this out, but I think this will make it clear that here, figuring out that variance is easy, and thus getting a standard error is not that hard. Here, figuring out that variance is non-obvious at first glance, at least not to me, because I'm not too smart. So I think we can see if we moved on to other functions, it's only going to get worse, this idea of trying to calculate the variance of the estimator so that we can make a confidence interval. So that's where we're going to stop for this video and this week if you're taking 510. But we pause to say, this is the idea that we're going to tackle next week. So this week, we introduced a very generic notion for if we have some random sample, we can estimate the distribution function for the distribution it came from. What we want to do next time is say, well, we have these estimators for which we don't think we're going to be able to calculate a variance easily, but we still want to make a confidence interval. How do we get an estimate for this variance? And we'll introduce a technique that's sort of similar in style, which is that, well, it makes very little assumptions and you can sort of just always use it, which I think is very useful. Okay, so that's it for this video. So as always, if you made it to the end, good job, and I'll see you in the next one.